Hey, this is a pre-calculus video on 9.6, mathematical induction, where we'll go through mathematical induction proofs. Basically, in this video, I'll give you the outline for any mathematical induction proof, and then I'll also go through a couple examples, and that'll help you with your homework on 1 through 10, the first homework assignment. So first of all, the principles of mathematical induction. Here's an outline for what you'll need to do. You'll let P sub n be a statement about an integer n. Then P sub n is true for all positive integers n, provided the following conditions are true or are satisfied. So what you're going to do is you will make your P sub n statement. Basically, that's what you're trying to prove. The first step will be for you to show that P sub 1 is true. Generally, you'll do this by plugging a 1 in for the n's and showing that that equals whatever the first term should equal. Your second step will be to assume P sub k is true. Basically, to do this, you're going to replace any n's that are in your P sub n statement with k's. What this represents is some spot, some place between the first term, or P sub 1, and P sub n. We don't know where exactly, but we're just going to assume that someplace along the way our statement is true. And then the big step, step 3, we're going to prove that P sub k plus 1 is true by adding the k plus first term to both sides and then simplify to show that it's equal to the right side of P sub k plus 1. So basically what's going to happen here is, assuming that P sub k is true, we are going to prove that the next term would be true. And because of that, we can then conclude by mathematical induction that the P sub n is true for all integers where n is greater than or equal to 1. So the idea behind this is, if we assume that someplace along the way P sub k is true, and wherever that is, if we can prove that the term after that would be true, then our P sub n statement has to be true, because we can then apply that logic to the first statement that we already showed was true. We showed P sub 1 is true, so by the logic in finding the next term to be true, we could say P sub 2 is true. Apply that same logic to P sub 2 to get P sub 3 to be true, and so on and so forth. So here's the first example we'll talk about. We want to prove P sub n equals 1 plus 3 plus 5 plus ... plus 2n minus 1 equals n squared is true for all positive integers n. So basically what you can see here is we have a series, and that 2n minus 1 right here is kind of the rule to get the nth term. And then that's set equal to n squared, which means that if you add all the terms up through n, you'll get a value of n squared. That's our P sub n statement. So now the first step, and you need to write everything that I've written in black. You need to show that the P sub 1 is true. Well, to get P sub 1, we would need to plug a 1 into 2n minus 1. That's the rule. So by plugging in a 1, I should get the first term. It's important that you realize you plug in a 1. It's not that the first term is 1 and that's why I'm plugging in a 1. It's that it's the first term. It's the nth term, the n being a 1. If this number was a 4, you'd still plug a 1 in here. So I plug a 1 in there, and I plug a 1 in for this n, and then I show that the statement does work, that P sub 1 is true. Next, I assume that P sub k is true. Again, this is where I'm going to take, and I'm going to rewrite the P sub n statement, replacing all the k's, or all the n's with k's, assuming that this is true. That brings me to the third step, which is where I need to add the next term. So whatever term would come after this, I need to add that to both sides of the equal sign. So what I would do is, to get the next term, if this is the kth term, I would need to add a term that has, instead of a k here, a k plus 1. That's what I've shown here. I'm going to add that to both sides. If I simplify that out, I get 2k plus 1. So what I'm going to do is I'm going to add 2k plus 1 here and here. Now once I do that, that would represent the p sub k plus 1. At this point, I am done with the left side of this equation. My goal now is to get this right side, this k squared plus 2k plus 1. I need to show that this would equal this if instead of plugging in a k, I plug in a k plus 1. So I'm going to set those equal to each other. All I did was I brought this down here, and I plugged in a k plus 1 for k, and brought that down here. Multiply that out, and you can see that statement is true. By mathematical induction, I have just proven that p sub n is true. How did that work? Well, I showed p sub 1 worked. I then assumed that somewhere along the line p sub k would be true. Assuming p sub k was true, I then proved that the term after p sub k was also true. Or if I go out to the term after the kth term, that the statement is still true. So now, since that worked, and since the first term worked, the p sub 1 worked, then the term after the p sub 1 term would also have to work from my logic shown in my p sub k plus 1 work. And I can keep applying that logic to show that it will work for every integer. So that's our first proof by mathematical induction. You might want to also add in here, it was written up above, but this right here, this means therefore when you have 3 dots in the shape of a triangle. Therefore, p sub n equals 1 plus 3 plus 5 plus dot dot dot. That's the original statement where n is a positive integer. All right. So numbers 1 through 4 and 9 and 10 all use this type of logic when working through your proof. Number 5 in your homework, the instruction was state an explicit rule for the nth term of the recursively defined sequence. Then use mathematical induction to prove the rule. So in looking at this, you should see, if you know that a sub n equals a sub n minus 1 plus 5, and a sub 1 is 3, you should recognize this right here as an arithmetic rule to get an arithmetic sequence, since you're adding that d, that 5. So this is a recursive rule. I need to state an explicit rule. So I use what I know about my explicit rules for an arithmetic sequence, where you take a sub n equals a sub 1 plus n minus 1 times d, that common difference. Multiply that 5 through, combine your like terms, and you get the statement we're trying to prove. We're trying to prove that a sub n equals 5n minus 2. So we can use what we know, that recursive rule, and a sub 1 equals 3, and we try to prove a sub n equals 5n minus 2. So then from there, the first step is to show that p sub 1 is true. Well, a sub 1 would equal, this is where I would take the rule that I'm working with here that I'm trying to prove, plug a 1 in for n, and I show that I get 3. How do I know that that's true? Well, remember, I was given the first term is 3, so I just showed it works for p sub 1. Now assume p sub k is true. Well, to get p sub k, I just replace the n's with k's. So a sub k would equal 5k minus 2. Step 3, I need to show that p sub k plus 1 is also true. Well, how would I get p sub k plus 1? This is where you've got to think about what you're working with. This is saying, how do I get the next term? I have the a sub k term is 5k minus 2. Well, if you think back to what we were told at the beginning, this recursive rule tells us if I have the previous term, I add 5 to it to get the next term, which means I should be able to add 5 to my a sub k to get a sub k plus 1. So that's what I do. If I simplify that out, I get 5k plus 3. My a sub k plus 1 should equal 5k plus 3. Now, if I plug in a k plus 1 to my a sub k, and I get the same result as when I add 5 to that term, that's going to show that, that's going to prove by mathematical induction that my rule is true. So I'm going to take, I might as well show the rest of this. I'm going to take and plug in a k plus 1 into this statement I have here, simplify it out, and since I got the same answer here and here, I've proven then, therefore, by mathematical induction that P sub n is true for all integers n greater than or equal to 1. And that's how, what is it, 6 through, no, maybe 5 through 8 on your homework assignment will go. So good luck, keep working, and try to come to class tomorrow with all the problems 1 through 10 completed.